So here today we'll see this unit unit 10. So in which we have the topics like vector atom model, and as well as we have topics like LS and JJ coupling of two electron states are there. So first we will be discussing about the what is vector atom model, and that we are going to be discussing. So this vector atom model actually we have got by the introduction of the spin into the formalism. That means when we take into account of the spin of the electron, so this vector atom model has been led. So that is by considering the spin of the electron, we have led to the vector atom model. So already we have discussed about that whenever the electron is revolving in orbital, so like if electron is revolving in this orbital, so center you will be having the nucleus. So the electron will be revolving in this orbital, in this elliptical orbit, it is revolving actually. So whenever it is revolving in the orbital, so it is going to be consisting of both spin angular momentum and as well as this what we call orbital angular momentum. Both you are going to be combined here. So whenever there is a spin of the electron as well as the that is orbital and spin angular momentum, whenever we are going to be combined, so we are going to be see the changes in the spectral features of one electron atom. So by considering the spin angular momentum as well as the orbital angular momentum, by combining these two, there are some changes in the spectral features of one electron atom. So that how the spectral lines are going to be changes, that is what we have to see in the vector atom model. So as we have discussed that the electron in an atom has both an electron in the atom, it is having both orbital angular momentum L and as well as the spin angular momentum S. So it is consisting of both orbital angular momentum, this orbital angular momentum, that is consisting of this orbital angular momentum. Generally, we'll represent with the L, capital L, we are going to be represent. And it is also having this what we call a spin angular momentum. So this spin angular momentum, spin angular momentum. So it is consisting of both the spin angular momentum as well as orbital angular momentum. So spin angular momentum generally it is represented with the capital S, we are going to be representing. So by combining these two, like a orbital angular momentum and spin angular momentum, by combining these two, we are going to get this total angular momentum J. We are going to get. So by combining these L plus S, we are going to get, which is calling it as a total angular momentum. We are going to call total angular momentum. So generally, this total angular momentum is represented with the capital J. So this J is nothing but J is equals to the combination of the orbital angular momentum as well as the spin angular momentum we are going to be. So we will see what will happen when this electron is in normal field. Otherwise, whenever it is going to be introduce the magnetic field, how it is going to be changes, what are the quantum numbers which are going to be get in these behavior of the electron we are going to be seeing here. So first, to describe the motion of this electron, we require some quantum numbers should be know. So if we know the quantum numbers, then only we can describe. So the principle, the first quantum number which we are going to get in this part is the first one which we are going to get is the principal quantum number. So generally we'll represent this principal quantum number with n. So we should know about the principal quantum number. This principal quantum number, generally it is represented with the small n we are going to represent. So it is identical with this principal quantum number, whichever we have been used in the Bohr's Sommerfeld theory. So that is what it is going to be have. And this principal quantum number, it is going to be takes the integral values starting from 1, 2, 3, and so on. So it will take all the values like starting from 1, 2, 3, and so on. You are going to be having here. Okay. So now that is about the principal quantum number. Then after we will be having another quantum number which we are going to be call it as a orbital quantum number. We have a orbital quantum number. This is orbital quantum number. About this also you should know. This is the orbital quantum number. This orbital quantum number is generally represented with the small l. We are going to be representing. Okay. So if you take this orbital quantum number, this orbital quantum number can take it can be take the integral values of in between 0 to n minus 1. It is going to be have. It's going to be take between 0 and n minus 1. In between 0 and n minus 1. So orbital quantum number is represented with L, and it can take any integral values between 0 and n minus 1. Suppose if you take one example, if you take, suppose if you have a n value is equals to 4. Suppose n value is equals to 4 if you have, then it can take the values like starting from 0 to 3. Like it can be take the value 0, 1, 2, and 3. Okay. All these 3, 4 values it is going to be take because orbital quantum number L, it is going to be take the values in between 0 and n minus 1 we have been called. So in between 0 and n minus 1, it is going to be take here. So as we have taken one example that if you take n is equals to 4, it is going to take the values from 0, 1, 2, and 3. It is going to be take here. So this orbital quantum number is somewhat similar to azimuthal quantum number k, and it is related by that k like L is equals to k minus 1. Okay, it is related by azimuthal quantum number, which is like L is equals to k minus 1. It is going to be half. Okay, so now this orbital quantum number. Uh, So it can take k value is equals to L is equals to k minus 1. It is going to be take. And the orbital angular momentum generally will represent with the PL. Orbital angular momentum will represent with the so now for us. I told that as it is going to be take n is equals to 4, it can be take 0, 1, 2, 3. And this orbital angular momentum, orbital quantum number is represented with L, and the orbital angular momentum, it is represented with the PL here. Okay, it is represented with the PL, you are going to be represented. And the orbital angular momentum PL of the electron, generally it is represented with PL is equals to L into h by 2 pi. L into h by 2 pi, it is represented. The orbital angular momentum Pi of the electron is given by PL is equals to L into h by 2 pi, you are going to be having. And since L can takes the integral values, like it is going to take any integral values, the magnitude of the PL is also quantized. The magnitude of the PL is also quantized. And according to the wave mechanics, the orbital angular momentum is having the values like root of L into L plus 1 into h cut. Otherwise, we can write h by 2 pi. So it can take the values the root of L into L plus 1 into h by 2 pi. So by convention, for an electron, L is equals to 0 is called S electron. So if L is equals to 0, it is going to be called it as a S electron we are going to be called. And similarly, if L is equals to value takes the 1, then it is going to be called it as a P electron it is going to be have. And similarly, for L is equals to 2, it is going to take the D electron. And similarly, for L is equals to 3, so it is going to be have the F electron. So like this, it is going to be take different values. Okay. So that is about the orbital quantum number L we are going to have. Then after this orbital quantum number, then we have the spin quantum number also. So generally the spin quantum number is represented by S. Okay. It is going to take a spin quantum number. Spin quantum number here. So this is represented with S you are going to be have. So the magnitude of the spin is always, its value is always equals to half you are going to be have. That is the spin of the electron. Spin in the spin quantum number, the spin of the electron is always half you are going to be have. Okay. So as for spin was assumed to be explained the experimental observed facts, but later on Dirac's mechanical treatment gave the theoretical justification that the spin angular momentum is going to be half Ps. Spin angular momentum is going to be half Ps, which is equals to S into h by 2 pi you are going to be. And where S value is going to be half we are going to be take because the spin of the electron is half we are going to be have. And according to the wave mechanics, this PS magnitude, that is the magnitude of this PS can be written as a PS is equals to, we can write it as a root over S into S plus 1 into h by 2 pi we can write. Okay, root over S into S plus 1 into h by 2 pi we can write. That is of the spin quantum number. And one more quantum number which we are going to be getting, this is the total angular quantum number we are going to be called, which is a total angular quantum number. Total angular quantum number. This total quantum number is represented with the J here. Okay. Total angular quantum number is represented with J here. So this total angular quantum number refers to the resultant angular momentum of the electron due to both orbital and spin motion. As we have talked about, when electron is revolving around the nucleus, it's going to be revolve in the orbital. So it is going to be have the orbital revolvement and as well as its spin. So by combining these two, resultant angular moment of the electron is due to the both orbital as well as the spin motions. It is going to be have the orbital motion and as well as the spin motion whenever it is revolving around the nucleus. So therefore, here we can take the resultant value as the vector sum of both L and S. Okay, here in order to get this total angular quantum number, we will be taking the vector sum of both what we call a spin as well as the orbital motion of the electron. So that is nothing but J is equals to L plus S we are going to be have. J is equals to L plus S. And the value of J is naturally half integer you are going to be have. Since one of its component S is equals to half you are going to be have. So it is usually expressed, its value is usually expressed in terms of like J is equals to L plus or minus you are going to be expressed. Going to be expressed in terms of J is equals to L plus or minus. So the plus sign is nothing but it is always parallel to the L vector you are going to be have. So when we are going to get this plus sign means this plus sign you are going to be getting whenever this field is parallel to the L vector. That is mm, parallel to the L vector, and minus sign you are going to get whenever it is anti-parallel. So S is anti-parallel, we are going to get the minus sign. So that is the reason why we will express this J is equals to L plus or minus S we are going to express. And the total angular momentum of the electron generally represented by the PJ here. So this is a total angular momentum, total angular momentum. So this total angular momentum of the electron represented with the Pj here. So this Pj is given by actually root over J into J plus 1 into H by 2 pi here. Okay, H by 2 pi here. So these are the some quantum numbers as well as their magnitude. Like we have seen about the principal or a total quantum number which is represented with n we have seen, and also we have like orbital quantum number L is there, and L can be takes the values from 0 to 0 and n minus 1 you are going to be have. So for example, we have seen when n is equals to like 4 if you are having, then it can takes the values from 0 to 3, 0, 1, 2, 3, and the magnitude of angular momentum is given by root over L into L plus 1 into H by 2 pi we have seen. And for L values, it can be take different like 0, 1, 2, 3 you are going to be take. So if L is equals to 0, then we will be calling it as a S electron we have called. And when L is equals to 1, we will be calling it as a P electron. And when L is equals to 2, you are having, we will be calling it as a D electron. And when L is equals to 3, it is a F electron we are going to be calling. So that is about the orbital quantum number. And also we have like a spin quantum number S. Okay, spin quantum number. So this is the spin quantum number S we have been called. And the magnitude is always taken it as a half always. In the beginning, we have said that value is a half for a spin, and it was assumed to explain the experimental observed fact. But later on Dirac's wave mechanical treatment gave the theoretical justification also. So the angular momentum PS, the angular momentum PS is given by S into H by 2 pi, where F is equals to half you are going to be have. And its value PS is equals to, we are going to written as a root over H into S plus 1 into H by 2 pi we have been written. And then after we have total angular momentum quantum number J. So its total angular momentum J, it results actually the angular momentum of the electron due to the what we call orbital as well as the and spin. So the combination of the orbital and total angular momentum of the electron due to both orbital as well as the spin you are going to be have. So therefore, generally the numerical value can be get as a vector sum of these two, that is J is equals to L plus S we are going to be get here. Okay, and value of J naturally you are going to be get a half integral you are going to be get. So by half integer we are going to be get. Since one of its component S is always having half value. So generally it can be expressed as a J is equal to L plus or minus S we can represent here. So this is represented with J is equals to L plus or minus S here. So we will be getting this plus sign in one case, and we are getting this minus sign in another case. So this plus sign is when S is parallel to this L vector, and this minus sign you are going to get when S is in anti-parallel to this L you are going to be get. And the magnitude, like the total angular momentum of the electron is given by Pj. So this Pj is equals to, we have like a root over J into J plus 1 into H by 2 pi you are going to be. So these are some quantum numbers which we are going to be arises when the electron is revolving around the nucleus, that is due to the orbital motion and as well as the spin motion of the electron. And moreover, so if this atom, whichever we have, if this atom is placed in a magnetic field, okay, if this is placed in a magnetic, previously whatever we have studied, like these all, when we are not placed in a magnetic field, in general, whenever we are going to be we studied all these spin quantum number, orbital quantum number, and as well as this total angular quantum number. And suppose if you take this atom into a magnetic field, so there is nothing but when atom is placed in a magnetic field, the field exerts a directive influence on both orbital and as well as the spin motions. That is nothing but when we placing in a magnetic field, automatically due to the magnetic field, there will be some changes in the orbital motion and as well as the spin motion of the electron is going to be takes place. So when we place in a magnetic field, due to the orbital and spin motions, which constitute certain what we call elementary magnets, uh, there are some more quantum numbers will be associated with this electron. That is nothing but when we place in a magnetic field, the orbital motion and as well as the spin motion of the electron is going to be affected, and this orbital and spin motion, which constitute certain what we call elementary magnet, three more quantum numbers we are going to be involved or otherwise associated with these what we call electrons. So what are those quantum numbers which are going to be associated when this atom is placed in a magnetic field? We'll see here. So the first quantum number which we are going to be getting this is a magnetic orbital quantum number we are going to get. So the magnetic orbital quantum number generally we will represent with mj here. So when we place this atom into a magnetic field, so as the orbital motion and spin motion both are affected, and this orbital motion and as well as the spin motion, which constitute the elementary magnets. So there are three more quantum numbers which are associated with these electrons. What are those? We'll see here. The first quantum number which is associated when electron is placed in a particular magnetic field, we are going to get this magnetic orbital quantum number mj. So we are going to get this magnetic orbital quantum number. Magnetic orbital quantum number. Orbital quantum number mg. Okay. Magnetic orbital quantum number mg. So this is associated with the electron when we have kept this in a magnetic field. So this is the numerical value of the projection of the orbital vector L on the field direction. Okay, this is the numerical value of the projection of the orbital vector L on the field direction. So ML is an integer, and many it may have only any values, any values of like 2L plus 1 values it is going to be taken here. Okay, so this magnetic orbital quantum number ML. So this ML can take many values like 2L plus 1 values it is going to take. It is going to take 2L plus 1 values. So which are starting from like minus L to plus L. Here includes 0 also. Okay, so including 0. Including 0, it's going to take ML can take the values like 2L plus 1 values it can take, and like from minus L to plus L, including 0, it is going to be high. Okay. And according to the space quantization, already we have studied about the space quantization. So according to the space quantization, the orientation of L with magnetic field are limited and are determined by the fact of projection of L in the field direction. So which is assumed to be integral values you are going to be have. So for instance, if the vector L is inclined to the field direction at an angle of theta. Okay, vector L is inclined with the field direction at an angle of theta here. So generally, we have like so this field direction means in this direction you have the field here. In this direction field you have, and this L it is going to be inclined at an angle of theta here. This is an angle of theta you are going to be inclined. So generally the rotation will be in the cone shape. Already we have discussed this one. So this is what you are going to have. So this is nothing but the angle with which it is inclined. So this is the field direction B, otherwise H we can represent, and this is the direction of the L vector. So it is inclined at an angle of theta, and this is ML, magnetic orbital quantum number we are going to be called here. Okay. So with an angle of theta, it is inclined. So generally, its projection is given by ML is equals to L cos theta. You are going to be have ML is equals to L cos theta. Since ML has to be an integer and cos theta never exceeds unity, that means the maximum value of cos theta is equals to 1. You are going to be have the permitted values. Okay, the permitted values of ML are starting from minus L to plus L at an interval of like it is going to be have L, okay, into L minus 1 comma L minus 2. That means L minus 1, L minus 2, and so on. Like this, if we extend, it is going to be 1, and as well as it includes 0 also. It includes 0 and also takes the negative values like minus 1, minus 2, and so on. And you have a minus of L minus 1, and so up to minus L it can take. Okay, minus L it can take. So the possible orientations of the L vector relative to the field direction is also 2L plus 1. The possible orientations also going to be 2L plus 1. We are going to have. It's going to be have 2L plus 1. The possible orientation of the L vector related to the field direction is also 2L plus 1. You are going to be have. So, for example, if we take suppose if we take like a L value. So, for example, if you have L is equals to 1, if you are having, okay, L is equals to 1. What are the permitted values for L? If L value is equals to 1, then permitted values of L will be like a 2L plus 1. It should be 2L plus 1. That means it is going to be get it as a 2 into L value is 1 plus 1 you are going to get. So total 3 permitted values you are going to be having. Okay, for which L is going to be take, ML is going to be take 3 permitted values. So what are those 3 permitted values means including 0, it is going to be have like a plus 1 it is having as well as a 0 and as well as it is going to be have minus 1. Okay, suppose if L is equals to 2, if you are having, okay, L is equals to 2, then the permitted values, okay, permitted values of L, permitted values of L will be like a 2L plus 1. So 2L plus 1 means L value is 2, so it will be 2 into 2, 4 plus 1. So total it will be 5 values it is going to get. Okay, it is going to be permitted 5 values. Like ML value can be taken in case of L is equals to 2, like plus 2 it is going to be half, plus 1, comma 0, minus 1, and minus 2. So all these values it is going to be permitted here. Suppose if you see the permitted values of this in case of L is equals to 5 here, if you see what are the ML values. So if you see in the picture, so it will be like in this manner. Okay. So it's going to be have ML values including 0. So minus 1 will be there, will be minus 1. Minus 2 also will be there. And similarly, we have like a plus 1. So plus 1 you have, and as well as the plus 2 you have. So therefore, it can be represented in this manner. So minus 1, 2, 0, plus 1, plus 2. All these 5 permitted values, like first permitted, second one, third, fourth, and fifth permitted values you are going to be. So this is the angle with which it is going to be made here. That means when we take this atom, which is consisting of electron, into a magnetic field, so we have like a associated with this magnetic orbital quantum number. So this is the values which can be takes this 2L plus 1 values. ML can be takes 2L plus 1 values starting from minus L to plus L including 0 you are going to be have. And the direction, okay, and the direction of the vector L is actually inclined with the field. So this is the field direction you have. So with the field direction, it is inclined with a certain angle L as a theta. So this is given by ML is equals to L cos theta you are going to be have. Okay. And ML has to be an integer and cos theta never exceeds unity you are going to be have. Okay. The permitted values of ML will be including plus L, minus L, as well as the zero, including it is going to be have. For instance, we have taken one example, two examples we have taken. For L is equals to 1, 2L plus 1 values means 3 permitted values you are going to be get. And similarly, for L is equals to 2, the permitted values will be like 2L plus 1 means you are going to get 5 permitted values, plus 1, plus 2, 0, minus 1, minus 2, you are going to get. So this is what the permitted values you are going to be have. In the case of what we call magnetic orbital quantum number. Similarly, we will have another quantum number which is associated when we kept this electron or atom in a magnetic field. That is a spin quantum number. That means the spin of the electron also going to be affected when we kept it in a magnetic field. As we told that the orbital motion of the electron is going to be affected, which is associated with this magnetic orbital quantum number. Similarly, when we kept this electron in the magnetic field along with this magnetic orbital quantum number, it is also associated with the magnetic spin quantum number, ms, we are going to be got here. Okay, so we'll see that also. Now, as it is associated another quantum number, that is what we call it as a magnetic spin quantum number. We'll be calling it as a magnetic spin quantum number. Spin quantum number. Magnetic spin quantum number, which is represented with ms, is represented with magnetic spin quantum number is ms, you are going to be having. So this is the numerical value of the projection of the spin vector s on the field direction. This is a magnetic spin quantum number ms is nothing but this is the numerical value of the projection of the spin vector s on the field direction you are going to be having. And as we have seen about the orbital motion, that is magnetic orbital motion in magnetic field we have seen. So with the orbital vector L, the vector S also can take the values like a 2s plus 1. Okay, it is going to be permitted with the 2s plus 1 values. Otherwise, 2s plus 1 permitted orientations with respect to the field P you are going to be having. According to the spatial quantization, that is a space quantization we have seen. According to the spatial quantization, ms can have any of the 2s plus 1 values. Can have any of the 2s plus 1 values. Like a 2s plus 1 permitted values it is going to be have, and it can be have any one of the, otherwise any of the 2s plus 1 values it is going to be have, starting from minus s to plus s. In this, it excludes 0. It excludes 0 here. In the previous one, when we have talked about the magnetic orbital quantum number, in that case, it including the 0, it is going to be takes place. And here in the case of this spin quantum number, it can takes the 2s plus 1 permitted orientations it is going to be have. And at the same time, it can have any of 2s plus 1 values starting from minus s to plus s. It excludes 0. So because spin, we don't have 0. So generally we have the spin as a plus half minus 1 half. So excluding 0. That means that ms can take values, only 2 values it is going to be have. ms it is going to be have 2 values. Those are plus half and minus half here. That can take plus half and minus half it is going to be taken. And this is about the magnetic spin quantum number it is going to be have. So as we have studied about the magnetic orbital quantum number as well as the magnetic spin quantum number, we have to go through this magnetic total angular momentum quantum number also. We have to go through this magnetic total angular magnetic total angular momentum quantum number. Magnetic total angular momentum quantum number. So this is magnetic angular momentum quantum number. So generally it is represented with mj here. Okay, mj it is represented. So this is the numerical value of the projection of the total angular momentum vector j on the field direction. Okay. Since we are dealing with the single electron, J can have only half integral values. J can have the half integral values like J is equals to L plus S we are going to be called. And whatever may be the value of L it can take, but S value should be always plus or minus half it is going to be. So it will be plus or minus half. So automatically L is going to be like a 0, 1, 2, 3 or minus 1, 2, 3, whatever it is going to be take. But S value should be like we discussed, like it is going to be half plus half minus half. So it can take the plus or minus L plus or minus half. And consequences to this MJ must have only half integral values. This MJ, it must have only what we call only half integral values. Only half integral values can take. Only half integral values can take. Okay. So the permitted orientations of J with respect to the field direction are the permitted orientations in the case of the J will be with respect to the field direction will be 2J plus 1 it is going to have. It's going to be have 2J plus 1. And the MJ can have only values. These are 2J plus 1 is the field directions. That is nothing but permitted orientations of J with respect to field direction. This 2J plus 1. And this MJ can have only values. MJ can have 2J plus 1 values. MJ can have 2J plus 1 values, which are starting from plus J to minus J here, excluding 0. It is going to be have excluding 0 you are going to be have. So the quantum numbers ML and MS come into play only in very strong magnetic field. Okay, where the coupling between L and S is broken, while MJ is effectively in ordinary fields. That means you have weak magnetic fields. The coupling between L and S will be broken here. So the quantum numbers used to designate the quantum state of each of electron in a given atom. So we will we will take the all these quantum numbers whenever this electron is kept in a magnetic field here. So suppose here if you want to calculate what is the angle with which it is going to be kept in a magnetic field here. Okay. So as we know that J is equal to L plus S, we have. Okay. So as we know that the combination of these two orbital angular momentum and as well as the spin angular momentum. So which we have already written that J is equals to L plus S we can write. J is equals to L plus we can write. So J can have like a root over J into J plus 1, J into J plus 1 here. So we can write mod of J is equals to, we can write it as a root over J into J plus 1 into H by 2 pi we can write. And we said that it can take the values, permitted values are from minus J plus 1, minus J plus 2, J minus 1, all those we have seen. Suppose in the case of this, how the direction will be there, vector addition of L and S will be there in case of, as we know that the spin of the electron is half or minus half you are going to be have. So J can be written as actually L plus S we can write, otherwise J is equals to, we can write it as what, L minus S we can write here. Okay, J is equals to L plus S or J is equals to L minus S here, because S can take the values of plus half minus half. So we can write J is equals to one case, we can write it as a L plus half, we can write. In another case, J is equals to, we can write it as a L minus half, we can write here. Okay. So if L is equals to 0, we'll have only one value. So for L is equals to 0, it has only one, J will have only one value, that is half we are going to be have. Suppose if we take L is equals to what we call 1, if you take the quantum number can take the values like J is equals to 1 is L plus 1, that is 1 plus half, because L value is 1 we have taken. 1 plus half we are going to get it as a 3 by 2, one case you are going to get. In another case, when J is equals to L minus half, L value is 1 and spin value is minus half, you are going to be half. So it can going to get it as a half we are going to get. So for this L is equals to 1, we have called whenever L is equals to 1, we have called it as a S electron, P electron we have been called. Okay. This for P electron, it is going to be have like a minus half, that is P by 2, and as well as the half you are going to be have. And similarly, for a d electron, so generally for a d electron, we called it as L is equals to 2, we have been called, and S is equals to, we have only one value, that is plus half or minus half you are going to be have. So in this case, J is equals to 2 plus half is nothing but you are going to get it as a 5 by 2 you are going to get, or you are going to get it as a 3 by 2. When L is equals to 2 and S is equals to half, we are going to be have. So generally, the vector addition, in the case of this, you can be taking it as that is nothing but when L and S are what we call aligned in a same direction. When L and S are both are aligned in a same direction, like this is L if you have been taken, and S is in this direction if you are having L and S, and the combination of these two, you are going to get it as a J here. So generally this J is equals to L plus S you are going to be have. Suppose when S and L are aligned like anti opposite directions if they are. So suppose if L is in this direction if you are having, and S is in this direction. Okay, S is in this direction. So here both are not in the same direction. They are aligned in this direction. So then we can write J is equal to this one. So here in this case, J is equals to L minus S you are going to get here. Okay. So the motion commonly used to describe the states here. Right. And here, if you want to calculate the angle with which it is going to be have. Okay. So we will be calculating what angle with which it is going to be take. That means along the field direction as we have drawn, like if this is the field direction if you are having. So this is the field direction if you are having. J, suppose L vector is in this direction. So it is going to be have theta is nothing but this one. Okay. And similarly, S is going to be spin of this electron. So L is in this direction. It is making with the vertical field direction. So we'll be calculating that theta also here. Okay. So here the angle between L and S we can calculate here. Okay. So the angle between L and S. Angle between L and S vectors we have to calculate here. Okay. So we have like a J is equals to, what is that? J is equals to L plus S we have written. That is nothing but total angular momentum will be equals to the combination of the orbital angular momentum and spin angular momentum here. So therefore we can write J square. J square is equals to, we can write L plus into L plus. Okay. L plus into L plus we can write. So here we are going to get J square is equals to this L square plus L square plus 2L dot S we are going to get. J square is equal to L square plus S square plus 2L dot S you are going to get. So this we can write it as a J square is equal to L square plus S square. We can write this as a 2L S cos theta we can write. 2L cos theta we can write. Therefore, cos theta is equal to, we can write it as, so if you write this, rearrange these terms, J square minus L square minus S square you are going to get divided by 2LS. So this theta, okay, this theta, where theta is the angle between the L and S, okay, L and S you are going to be having. So this is how we can calculate this theta, the angle between L and S we can take here. So since the eigenvalues of square of angular momentum is J square, L square, and S square, so we can get we have written that J is equal to root over J into J plus 1 into h by 2 pi we have written, and similarly L value we have written it as a root over L into L plus 1 into h by 2 pi we have written. Similarly, S value we have written as a root over S into S plus 1 into h by 2 pi we have written. Therefore, if you want to get j square, so it will be simply j into j plus 1 into this what we call h by 2 pi you are going to be get here. H by 2 pi whole square. Otherwise, simply we can write it as h cut whole square. Similarly, L square I'm writing. So this L square value are going to get as L into L plus 1 into this h cut I'm writing instead of h by 2 pi. H cut whole square you are going to get. Similarly, the S square value we are going to get it as a S into a small s this one, S into S plus 1 into h cut square you are going to get. So from this, if you calculate the angle which is present between this L and S can be calculated, so that we are going to get it as a cos theta, which will be equals to like a j into j plus 1, because j square is this one. All this h by 2 pi it is going to be get cancels. 1, 2 it is going to remains. So it will be j into j plus 1 minus L into L plus 1 and also minus S into S plus 1 you have divided by this 2 into you are going to get the root of L into L plus 1 into root of S into S plus 1 you are going to get. So this is the cos theta. Okay. If suppose if you take the phi is the angle the j vector makes with the z axis, then we can write it as a cos phi. What is this is? If phi is the angle between what we call j vector which makes with the z axis, we can write it as a cos phi is equals to jz by j we can write here. Okay. Jz is equals to sorry, cos phi is equals to jz by j we can write here. Okay. So this is about the what we call vector atom model. That means we have discussed the vector atom model in such a manner that whenever we will take in this what we call spin angular momentum. That means the orbital motion of electron and as well as the spin motion of the electron, both if you take into consideration. So when we not taken into a field, that means when we are not taken into a field, we are going to be get different quantum numbers we are going to be associated, and also when the electron is taken into the magnetic field, it is going to be changed. It's due to the magnetic field, it is going to be changed. Some effect will be there on that one. So due to that, it is going to be get this magnetic orbital quantum number ML you are going to get, and similarly we are going to get a magnetic spin quantum number MS we are going to get, and as well as the by combining these two, we are going to get the total angular momentum mj. And also we have calculated the theta, the angle between this L and S, whichever we have been calculated, that is cos theta we have been calculated. So this is what we call a vector atom model, which we have. Right. Next, we will be moving into another topic, which is the LS and JJ coupling of two electron states. Okay, so we'll be studying about this LS and as well as the JJ coupling. The next one we have is LS and JJ coupling. LS and JJ coupling. So the addition of angular the addition of this orbital and spin angular momentum for many electron atoms, it is much more involved than that of an single atom electron. So suppose if you take only one electron is present, and if you are talking about the that electron orbital motion and as well as the spin motion of that electron, if you are talking, so you'll be having simple thing. But when we are having what we call this addition of this orbital and spin angular momentum for many electron atoms, so it is much more involved than that of a single electron, that is one electron. So for many electron systems, only the electrons outside a closed shell, which we will be calling it as a valence electrons, we are going to be calling. So for many electron system, only the electrons which are in the valence state, that is valence electrons, will contribute the angular momentum of the atom. Okay, so that is when we have taken so many electrons into account. So for many electron system, only the electrons outside a closed cell, which we are going to be call it as a valence electrons, we are going to be called. So these valence electrons contribute to the angular momentum of the atom. That is what we have to remember. That is, when we are studying about the many electron system, only the electrons which are present in the valence shell, which we will be calling it as the valence electrons. So these valence electrons will contribute to the angular momentum of the atom. Okay, angular momentum of the atom. So to proceed this available to compute the total angular momentum J, of many electron system, this LS coupling and JJ coupling schemes we have to study here. LS coupling and as well as the JJ coupling. So first we will move to this LS coupling. So what is LS coupling? We'll see here. LS coupling. So this LS coupling is also known as, we will be calling it as a Russell-Sanders coupling we are going to call. This will be calling it as a Russell-Sanders coupling. So this LS coupling is also known as what? Russell-Sanders coupling we are going to be called. Okay. So here, since an atom consisting of a large number of electrons, so as atom is consisting of 1 minute. So since the atom is consisting of a large number of electrons with different orbital and spin moment, the coupling or interaction schemes is necessary to obtain resultant orbit and spin momentum of an atom as a whole. That means, as we know that atom is consisting of what we call large number of electrons. So the orbital and spin momentum coupling or interaction scheme is necessary to obtain the resultant orbit and spin momentum of an atom as a whole. Okay. So these coupling schemes, as I told, that there are two types. One is LS coupling and JJ coupling. So first we will be seeing this LS coupling. So this LS coupling is a common type of combination in which several L vectors will combine with several L vectors will combine with combine of what we call to form a resultant L you are going to form. And similarly, several spin vectors likewise combine to form a resultant vector S here. Okay. So several L vectors will combine to form a resultant capital L, and similarly several spin vectors likewise combine to form a resultant vector S here. So the resultant L and S then combine to form a resultant J, which represents the total angular momentum here. So initially, when we take this combination of several L vectors, so generally, suppose if you take like a L vectors, if you are having L1 plus L2 plus L3, okay, plus L4 and so on here you may be having. So which will be combined to give a L vector, which is capital L we are going to be called. And similarly, several spin vectors like a S1, small s1, S2, S3, S4, and so on. So these will be combining to form a capital S here. Okay, then after combining these two, we are going to be get this L plus S J vector you are going to be get. So that we can write it as a combination of these two, that is J is equals to L plus you are going to be have. This L is nothing but a combination of all L vectors, which is L1 plus L2 plus L3 and so on. And similarly plus S vectors, that is S1 plus S2 plus S3 and so on here. Okay. So by combining these, we are going to get this what we call L combination of L vectors and S vectors. We are going to get this J vector here. And this these are quantized. Certain quantum rules are must be followed. Okay, to forming these resultant J, some quantum rules are going to be followed here. So the first one, what we have here, it is first one, which we have is all three vectors L, S, and J must be quantized. The first thing is all three vectors L, that is the orbital quantum vector, orbital motion of the electron, and S, spin motion of the electron, due to which we are going to get this vector, and also the combination of these two vectors, you are going to get this J. So all the three vectors L, S, J, they must be quantized. That is what we have to do. They must be quantized here. Okay. And the second point which we have is L, capital L, it may have the values like starting from 0, 1, 2, 3, and so on. Okay, depending upon the number of electrons in the atom and the direction of their orbital vectors. Okay, the direction of their orbital vectors. So suppose if in the case of L is equals to 0, we will represent in this manner. In case of L is equals to 0, we will represent L is equals to 0 means this is what we represent in the orbital vectors. Okay. And in the case of L is equals to 1, generally we have this. Both are in the same direction. This is the resultant vector J. So L is equals to 1 we have. In the case of L is equals to 2, both the same direction like this. L is equal to 2 you are going to get. Okay, depending upon the number of electrons in the atom and the direction of their orbital vectors will be there here. So next, this has to be follow another rule in order to form this LS coupling, which is here. Okay, so S, third one here, S may assumes to have the values. S is nothing but that is due to the spin motion of the electron. So as we know that spin motion, it may be having like a half. So S may be assumes to have, S may assume values like a 0, half, 1, okay, 3 by 2, 2, and so on. Okay, it may assumes the values like a 0, half, 1, 3 by 2, 2, and so on. It is going to be have depending upon what color number of electrons in the atom. Okay, depending upon the number of electrons in the atom and the direction of their spin vector also. So how many number of it may takes all these values like a 0, 1, 2, 3, whatever it may be. It may depend upon the what we call values of number of electrons which are present in the atom and also the direction of the what we call spin vector. Okay, direction of the spin vector. Suppose if you take an example to study this spin of this one. Suppose if an atom is containing a single electron. Okay, for example. Okay. Okay. So suppose if you have a example. Suppose if you have an atom which is containing a single electron, if you take an, okay, you take a single electron. So when you have a single electron, S can have only the value. S can have the only value that is half you are going to be. S can have only the value half you are going to be. Suppose for 2 electrons, okay, for 2 electrons. Suppose in an atom, if you are having 2 electrons, so S may be having like a values like it may be having 1 or 0. It may be having 1 or 0. That means if both spins are half, plus half, if you are having, then it is going to take plus 1. Otherwise, it may be having one is plus half, another one is minus half, means it is going to be take what we call 0. Okay, 1 you are going to get by combining these 2 electrons plus half, you are going to get as a 1. Suppose if you are having 1 plus half, another one minus half, it is going to be have 0 you are going to be have, depending on whether the spin vectors are parallel or anti-parallel. Okay, spin vectors are parallel or anti-parallel. It can take the 2 values like 1 or 0 for 2 electrons. Okay, similarly, suppose if you are having a 3 electron atom, suppose if you are having 3 electron atom is there. So in the case of the 3-electron atom, so S can take the values like it may be having like a 3/2 or 1/2 you may be having. Okay, it may be taking 3/2 or 1/2 because 3 electrons if you are having, if you depending upon the spins, it may be taking 3/2 or 1/2 it can take. Suppose if you are having a 4 electrons, you are having 4 electrons in an atom, the S can be take it may take like a value of 2, 1 or 0 it can take here. Okay. For 2-electron system, if you see generally how the orientation of this what we call S will be there. So for 2-electron system, we said that S can take 1 and 0 value. That is 2 electrons means if they are in the same direction, if they are in the same direction, so S1, which is S1, this is small S2. So you are going to get S is equals to 1, you are going to get plus of, you are going to get it as a 0. Suppose one is in this direction, okay, one is in this direction, another one is in this direction, one is parallel and one is anti-parallel if we are having. In this case, you are going to get S is equals to 0. So this is what representation of the 2 electrons. Okay, this is the representation of 2 electrons. In the case of the 3 electrons, we said that it is going to take either 3/2 or half you are going to do. So when you are going to get this means when it is a 3-electron system, suppose if all these 3 electrons, whatever they are, if they are in the same direction, if you are having all 3 electrons, so one is a small s1, another one is s2, another one is s3. So when you combine all these, that is plus half, another plus half, you are going to get it as a 3/2 you are going to get. Suppose in another case, 2 may be in one direction and another may be in the other direction. So in this case, you are going to get plus half 1 and it is having another half. You are going to get it as a overallly 1/2 you are going to get. So this is for what we call a 3-electron system. This is how it is going to be. In the case of the 4-electron systems, we said that it might take the values of 2, 1, 0, 1. So if in the case of the 4-electron system, the case of the 4-electron system, if you are having. In this case, if suppose all the 4 electrons are in the same direction like this, all the 4 electrons are in the same directions. So you are going to get plus half, another plus half. Total, it is going to be combined. You are going to get it as a 2 you are going to get. Suppose if 3 electrons in one direction, 3 electrons in one direction, another one is in the opposite direction if you are going to have. So it will be plus half, it will be 1, and it will be 3/2, and this is in the opposite direction. So it will be 3/2 minus half. It is going to get it as a 1 you are going to get. Okay. So plus half is 1, 1 plus half, we are going to take it as a 3/2. Another one is in the opposite direction, that will be minus 1/2. So it will be 2/2, 1 you are going to get. So that is what you are going to get. One more case you are going to get is you are going to get another one. Suppose if 2 electrons in this direction and 2 are opposite direction, this will be plus half 1, and this will be plus half 1. It will be 1 minus 1. It is going to be 0 you are going to get. And 1 you are going to get in another case also, that is 2, 1, 0, 1. 2 we have got, 1 we have got, 0 we have got here. Another 1 we have to get, that is suppose these 3 electrons are in this direction and 1 electron is in this direction. It will be minus half. It will be minus half, another minus half. So it will be 2 minus 3/2, and this is in the opposite direction. So plus 1/2. So it will be again. So you are going to get it as minus 2/2. This one. So magnitude is 1 you are going to get. Anyhow, it may be minus 1 or 1. So this is how the S may takes different values. Okay. So next one, what it should follow is in the case of the LS coupling. So next one is hence J vector. Okay. Hence J vector is the sum of L and S. Okay. Hence J vector is nothing but it is the sum of L and S. Already we have seen this. J is equals to L plus S. You are going to be have. So it must have the integer values. The combination of J will be having the integer values, like it may take 0, 1, 2, 3, and so on, whatever it may be, it is going to be take here. Okay. So if S is an integer and J have half integer of S is an half integer. Okay. If S is an integer, S is an integer if you are having, right? And J have half integer, suppose J has half integer of S is an half integer of integer. Okay. The possible number of values for J, which can assume will be again 2S plus 1. 2S plus 1. This is in the case when L is greater than S. And you may get 2L plus 1. This is in the case when L is less than S. Okay. So this is what LS coupling we have. Okay. So the quantum conditions which are imposed on this coupling are that J can have only non-negative values. Okay. J can have the non-negative values you are going to be have here. Okay. So this is since it represents the total angular momentum of the atom, as it is representing the total angular momentum of the atom. Okay. Suppose if you take any specific example to calculate this LS coupling, suppose if you take any specific example, suppose we consider an example, specific example, in case of one electron in a p orbit and the other in d orbit. Okay. So we'll be taking example, one electron, okay, one electron which is present in a p orbital, it is present in a p orbital, and the other is present in another electron, it is present in d orbital. Okay, another one is present in a d orbital. So we can have some values, the possible values which you are going to get here is, which L is equals to 1, 2, and 3 here. L is equals to 1, 2, 3. You can get, and S is equals to 0. Okay, S is equals to 0. So we have some possible values to work with. L is equals to 1, 2, 3, and S is equals to 0. So first what we'll do is we will be taking S is equals to 0. Okay, S is equals to 0, and L is equals to 1, 2, and 3 we are going to be taking. So we construct the vector diagrams here. We construct the vector diagrams here. So as S is equals to 0, J just equals to L. S is equals to 0, J equals to L values. Because why? Because J is equals to what we have, L plus S here. So what we have taken here, S is equals to 0 we have taken. So whatever may be the L value it is going to be take here. That means J is equals to 1, 2, and 3 you are going to have. In the case of S is equals to 0, J is equals to L plus S. S value if you substitute 0, J value you are going to get it as what? 1, 2, and 3 you are going to be get here. So in this case, J is equals to 1 means first case L is equals to 1. Here L is equals to 1 and S is equals to 0 here. J value is equals to 1 you get. Another case is L is equals to 2 we are going to take. S is equals to 0. J value you are going to get it as a 2 here. In another case, we have L value is equals to 3 we have, and S is equals to 0. In this case, J is equals to 3 you are going to get. Generally, it will be combination of these two in this direction. It is going to be. Okay, like this you are going to be having. Okay, and here with S is equals to 1, there are 3 possibilities. So previously S is equals to 0 we have taken. The 3 possibilities, whatever we are going to get is L is equals to 1, S is equals to 0, 1, 1. Case L is equals to 2, S is equals to 0. Another case L is equals to 3 and S is equals to 0. This is another case. Like this, we will be getting these 3 different cases we are going to get. And similarly, next when we consider uh, with S is equals to 1, with S is equals to 1. When we take S is equals to 1, there are 3 possibilities for each value of L. for each values of L. That means three L values you are going to have. S is equals to 1, 3. There are three possibilities for each of three L values. Okay, each of these L values. So L values, we know that it may have 1, 2, 3. L values may have 1, 2, and 3 here. Suppose if you consider L is equals to 1 and S is equals to 1 here. So J can be combination of L plus S, that is 1 plus 1. You maybe have like a 0, 1 as well as a 2 you have. So in case uh, S is equals to 1, L is equals to 1, it may have J is equals to 0, 1, 2. In case of L plus S, it will be 2. In case of L minus S, it will be 0. It have. So next one, in case of J is equals to, L is equals to 2 and S is equals to 1. In this case, J can take three different values, 1, 2, 3 here. 1, 2, 3, you can take. And similarly, in the case of L is equals to 3 and S is equals to 1 if you take. So in this case, J can get like a 2, 3, and 4. Okay, these four different values you are going to get here. So this is one of the examples we have. So this is about the LS coupling. So Russell's Sanders coupling we have. Next, we have one more type of coupling, which we calling it as a JJ coupling. We have another type of coupling, which we will be calling it as a JJ coupling. JJ coupling. So this JJ coupling here. Adore conditions. Hypothesis. Right. In the case of the JJ coupling, this coupling predominates in atom where the interaction between Li and Si is considerable. In this case, Li vector combines with the corresponding Si vector to give Ji vector. Okay, the total angular momentum of this electron we are going to get here. So we'll see here. So first, we'll determine all the various spectral terms arising from any given electron configuration in JJ coupling. The spin S of each electron is quantized with respect to L to form a resultant J, such that J takes what we call half integral values only. Here, J can take the half integral values here. The two J's are in turn quantized with respect to each other, which results a capital J here. Okay, such that J can take integral values only. Okay, so in this case, suppose we see what is JJ coupling. It's J1 here, which is due to L1 plus S1. Similarly, J2, if you take, it is L2 plus S2. Okay, and so on, you are going to be have. And this capital J is nothing but combination of all these J's, J1 plus J2 plus J3, and so on. You can write this summation of I, Ji, we can write. Okay, Ji we can write here. Okay. So which states that the states are denoted by the values of J1, J2, and by the J motion, that is J notation, which is given by J1, comma J2 of J we can write. Okay. So if you see the specific example in the case of the JJ coupling, for example, if you take S1 is equals to half we have, comma L1 is equals to L, comma S2 is equals to half, and L2 is equals to 2 if we have. Okay. And for the P electron, J1 is equals to 1 by 2 or 3 by 2. And for D electron, J2, which will be equals to 3 by 2 or 5 by 2. Okay. So combining these four values, all possible values of this you are going to get as all the possible values we are going to get as J1 is equals to half, and J2 is equals to 3 by 2, J is equals to 1, and 2 you'll get. Okay, by combining these all. From another one, J1 is equals to 3 by 2, and J2 is equals to 3 by 2 we take. By combining these, J can take 0, 1, 2, and 3. Okay, different values you can take. And similarly for J1, take 1 by 2, and J2, if you take it as a 5 by 2, by combining these, you may get the J values like 2 and 3 you can get. Okay, 3 you can get. Another combination which you are going to get is J1, if you take a 3 by 2, and J2, if you take a 5 by 2, then the J value is going to be get by combining these different values, you are going to get as a 1 you can get, 2 you can get, 3 and 4. Okay, J can takes 1, 2, 3, 4. Okay, this is exactly the same number of turns arrived in the case of what we call LS coupling scheme. Okay, and this is what resultant J we have. So today's class, what we have seen is we have studied that vector atom model we have seen, as well as the typical LS coupling, that is a Russell's Sanders coupling we called, and also JJ coupling, all these three we have studied. So in the case of the vector atom model, when we have taken into account the orbital angular momentum and as well as the spin angular momentum, whatever may be the quantum numbers which are associated with this one. When we have taken both these quantum numbers into account, the interaction is going to be the spectral terms, whichever you are going to be get, it is going to be seen here, and also the quantum numbers which are associated with these we have seen. So when we taken that atom is not in a magnetic field, without any magnetic field, we have associated with the like total quantum number n, it is associated. It is it can takes the values like 1, 2, 3, it can takes, and similarly we have orbital quantum number L when we have taken this into account. So L we have, so this L can takes the value in between 0 and n minus 1 we have called, and we have seen specific example. For if you take an n is equals to 4, we have taken, it can going to get the values like L can take the values like a 0, 1, 2, 3 it can take. Okay, and the orbital angular momentum have the value like root over L into L plus h by 2 pi. Similarly, the spin quantum number S we have seen. Spin quantum number is S we have thought. So this S can take only the values like a plus half as well as the minus half in the case of the electron. This is going to take plus half and minus half. Both values only it is going to be taken here. And we have seen that the spin angular momentum is represented with the PS and PS is equals to what we call SH by 2 pi we have, and the value, the PS value can be written as a root over S into S plus 1 into H by 2 pi. This is the value which is there. Okay, and by combining these two, spin angular momentum and as well as the orbital angular momentum, we have got a total angular momentum. We call it as a J. J is equals to L plus S we have seen. And this J also can take the values like a the total angular momentum of the electron PJ is represented with what we are going to get it is the value of J into J plus 1 into H by 2 pi you are going to get. Okay. Similarly, when we taken this into what we call into a magnetic field, when we have taken this into a magnetic field, we are going to be get three different quantum numbers which are associated with that one we are going to get. One is a magnetic orbital quantum number ML we are going to be get, and also we are going to get another quantum number which is called it as a magnetic spin quantum number MS we have got. And by combining these two, we are going to get this what we call magnetic total angular momentum quantum number MJ you are going to get. So that is what about the vector atom model which we have seen. The resultant quantized vectors are representing the atom as a whole. That is a combination of both orbital quantum number and as well as spin quantum number. The resultant quantized vector represents the atom as a whole, which can be obtained by combining these two vectors, individual electrons in the atom, and application of this rule to spatial quantization. That is what we have seen about the vector atom. Then we have seen these two couplings like LS coupling as well as this what we call JJ coupling we have seen. So this LS coupling is nothing but the combination of all vectors, all L vectors, several L vectors combined to form a resultant L vector. It is going to be combined, and similarly by combining the several spin vectors combined to form a resultant vector. The combination of these two, the resultant of L and S will combine to form a resultant J vector, okay, which represents the angular momentum of the atom. So we have got like a L1 plus L2 plus L3 and plus S1 plus S2 plus S3 and so on, plus S, which we call it as a J total quantum number. Okay, resultant J we are going to get. So for a particular value also we have seen how the direction of this it is going to be how for L is equal to 0, L is equal to 1, L is equal to 2 we have seen. And similarly we have like a S mate can takes the values like a 0, 1 by 2, 1, 3 by 2, 2, and so on we have seen. Okay. So by taking some specific example, we have seen this LS coupling we have seen. Similarly, we have the combination of this. We have seen the JJ coupling. JJ coupling is nothing but it's a combination of JJ coupling for two electrons you are going to get. All J's combinations you are going to get all another J's combination. By combining these two, we are going to get these different values. So this is about LS and JJ coupling.